Great. Hopefully that works. And this works. It works. Great. As you can see, I will do my talk in English. I had this idea for the expo. Last year we were here with a simulator, people could try it, and I figured this year I want to do something different. I somehow have a problem with doing the same thing twice. So I got myself into a lot of trouble by asking if I could do sort of a lecture thing, and they said yes, to my surprise. So I spent some days preparing something. What we'll talk about today, first a bit of an intro and a disclaimer. The topics are about acceleration, what is that, what does it mean, a fairly simple theory about it. Tires, extremely important of course to your racing car. Weight transfer, something we've all probably heard about if you're a sim racer and you've been reading stuff online. And then, well, driving with tire loads in mind is basically applying the stuff that comes before that to your driving. And then I put car setup tips at the bottom, because I think I mentioned in my announcement video it would be something about that. It's not really, so sorry if you expect to go 2 seconds quicker a lap after this. I'm afraid I have to disappoint you. It might happen, but it's unlikely.
Yeah, but the agents are racing, so you can get some of those setups today. It would be good.
Anyway, and I'm recording it. I'll put it on YouTube most likely if the camera doesn't fail, and if I don't fail. That's basically the thing. So get right into it. That's me, 1984, I think. Only time I was in a single-seater racing car. Since then it's all virtual. So a brief history from then to now. My dad came home when I was 7 with a PC, an XT. I don't know if you remember that. Some of you might be old enough. 4.7 megahertz. Now my PC at home runs at 4.7 gigahertz. And it's got 4 cores and all that, so things have come along so far. But I liked the racing games for some reason. Accolade, perhaps you remember Test Drive, Grand Prix Circuit, and I just loved those games. And I was also into Technic Lego, building cars and other mechanics and with pneumatics and motors and stuff. Very enjoyable. So I decided to do mechanical engineering in school. And I figured that's probably, if it's a bit like Technic Lego for grown-ups, suits me well. Then I had some boring jobs, and during those boring jobs, since about 2006, I got into R-Factor, which at first I didn't like, and then there came a phase where I was bitching about it on the forums. And then I figured, well, let's see if I can make it better. And since then I've slowly started to learn about physics and vehicle dynamics, and I was still a mechanical engineer, so I was making some pedals for myself from wood and stuff like that. So all the sim hardware and software stuff is basically, it started in 1984 and now I'm here, so that's fairly crazy. So, first a bit of a disclaimer, you're not looking at somebody who is God or who is an expert. Most of the stuff I know is self-taught. There's a lot of discussion everywhere, what is real, what isn't real, what is true, what isn't true. You won't hear me say that I know what's true. I have opinions, I realize I'm often wrong. So that's something to keep in mind. I think realizing that there is a chance you're wrong increases the chance that you might actually be right, but you can still be wrong. There will be some inconsistencies here. If there's a physics professor in the room, he will disagree with my use of units, but we keep it relatively simple. I leave things out and then I'll make mistakes. So let's cover my tracks before we start. Briefly about acceleration. What is acceleration? Not just accelerating forward, but acceleration can be in all directions. Braking you could see as negative acceleration. If you imagine a block of something that weighs 100 kilos and you put it on ice where there's no friction, magic ice, as long as you have a force acting on it, so you push it for example, if the force is equal to the weight of the object, you get a 1g acceleration. That's kind of, I like how that looks because that's okay. I can sort of visualize that. The force being equal to the weight of the object results in a 1g. So if you push with 200 kilos, you get 2g acceleration. Now, kilos and newtons and all the units, like I said, I'm keeping it simple. Kilos we understand. I think Oktoberfest is coming up and you have a lot of kilos. So that's to keep it simple. And then we have a racing car. Again, a simplified example, but if the racing car weighs 1,000 kilos, means we have to apply a force of 1000 kilo to make it accelerate or decelerate or corner at 1g. It's kind of, I think it's kind of sort of a logical thing, and it kind of makes it, oh, it's not that complicated what the g-forces do. Of course it is more complicated because you have aerodynamic drag, which, lots of stuff. We're going to forget about a lot of stuff today, so we're going to keep it as simple as possible, which might still be fairly complicated later on, but we'll see. First about tires, of course, extremely important. One of the major things when you talk about tires is the load that's on them. So that's nothing else than how hard the tire is pushed onto the road. So if a car weighs 1000 kilos and it's got even weight distribution, each tire loads the ground with 250 kilos. That's tire load. Simply how much force presses them down into the ground. And that's an important thing to decide how much grip the tire might potentially have. If it's not on the ground at all, there's no tire load, there's no grip, naturally. So, the thing that's most important here is something called load sensitivity. Basically says that if you double the load on the tire, you do not get double the grip. That's quite an interesting thing, and that's very important with what I want to explain later, because I think in the announcement I said, well, what about if you make a roll bar change to your setup? Why does that change the balance of the car? And this is the key to it, so we have to explain a bit what it is, how that works. And often the grip of the tire is expressed as a friction coefficient, and that's a number that you multiply with the tire load to get the potential grip the tire has. So if the tire has a friction coefficient of 1.5 and there is 100 kilo load on it, 1.5 times 100 means you have potentially 150 kilos of grip at that tire. So that's just a convenient way people often specify it. Because I want to do some actual calculations later to show you the actual difference in grip from a certain setup change, we have to put in some numbers. So this is a GT car, a tire, and the rule of thumb is that every 100 kilo of load removes 0.1 of that friction coefficient. And when there is no load, which is a bit strange, but imagine the tire is barely touching the ground, we can estimate the friction coefficient is about 2, which is quite a lot, but every 100 kilo subtracts 0.1 from that value. So at 200 kilos, you got 1.8 left. And that means load times that friction coefficient, 360 kilos of potential grip. And you can do the math. The more load, the lower the friction coefficient. And the grip still increases, but it doesn't increase at the same rate as the load does. Some people prefer graphs. So here on the left you see that the friction coefficient drops from 2 initially, and then as the tire load grows, friction goes down. And we can also express that in absolute grip, it's on the right. So the tire load grows, it's horizontal, and then the grip, vertical, it starts to flatten off because it doesn't like load. I think that's the best way to put it. Tires don't like being loaded heavily. They get less grippy. Well, that's the main thing to differentiate. The coefficient of friction goes down, but the actual grip goes up, just not as quickly as you would hope. The best example to give with this is applying a very simple problem to a car. Here, a light car weighing 1000 kilos, and we can do the math because now we know what the friction coefficient of the tire is. So we assume that it's all evenly loaded, so 250 kilos per tire. If you put that in on this line, you can see at 250 just about what sort of a friction coefficient we have, which is 1.75. And that means this car has a potential to do 1.75 G purely by tire grip. And each tire on the front we got 875 kilos of force, and on the rear, but of course cars have weight transfer and all that stuff will come. But this is an example of the theoretical grip a 1000 kilo car will have with the tire model that we just made. Okay, all great. Now we make the car twice as heavy. What happens is we get more grip, but the friction coefficient is lower. So by this point we have 500 kilos on each tire. And if we look up the 500 kilos in the downsloping curve, we get 1.5 friction coefficient. The total grip is then 3000 kilos, a lot more than 1750, but not double. So what happens is 3000 kilos of force acting on a 2000 kilo car is 1.5 G. So simply because this car weighs half as much, it pulls 0.25 G more theoretical maximum braking grip. So that's an idea of, okay, that's evidence that tire load is bad for cars, and you want the cars to be as light as possible. By the way, if at some point you think I'm talking nonsense or you have a question, you may ask. It's always fine, so don't hesitate. And like I said, it's secretly not a very good question, cut it out. So feel free to do that. I'll more or less go on, but feel free to interrupt, and we'll see if I know the answer to whatever your question is. We see now that load is very important. The heavy car had less grip than the light car, but load doesn't mean that there is grip. To get the actual grip, to get that potential out of the tire, you need to add some slip. Slip is, in this case, an example of a car driving away with wheel spin. At that point the tire spins fast, but the car is still almost standing still. So the tire spins faster than the car is actually going. And that slip creates friction and forces, the rubber rubs over the road and it drags the car forward basically. And you need a little bit of slip. So this is extreme, accelerating like this, but even if you're just driving on the street, every time you accelerate, even just at a leisurely pace with the groceries in the back, you get wheel spin. Not smoke, but the tire spins 1 or 2 or 3% faster than you're actually going at that point. That generates the grip. The theory behind that is complicated and I don't even understand it, but we have to assume that the tire has to slip. So the potential grip that we had in those examples, 1.5 G, 1.75 G, we only get that if we manage to get wheel spin that is about 10% different from the car speed. So when braking, we want to slow down the wheels 10% from the speed that you're going. It's important to realize. This ugly drawing is the other slip. So what we just had was braking and accelerating forward and backward. And cornering is called lateral slip. And this is expressed as the angle between where the car is going and the angle where the tires are pointing. And that also has to be a slight angle in order to rub on the road and start to pull the car around the corner. It's not super important to know a lot about it, but grip only comes from slip. So the load sets the potential, the maximum grip we can achieve, and it's up to you to get with the brake pedal, with the steering, to make the tires slip and to get that load. Sorry, to get that grip. And roughly it's a bit like this. So if there is no tire slip, 0% right at the bottom, we have no friction. The tire just rolls and the car, well, it will come to a halt because of air resistance and that sort of stuff, but eventually there is no force. We have to slip the tire to get the 100% friction that we calculate with that downsloping line show. That's quite important. And we can have pure braking or accelerating grip, we can have pure cornering grip, we can also combine them. However, you cannot have 100% braking grip and 100% turning grip at the same time. That would be nice, it would be a lot quicker, but in theory both can be present about 70%. So you can brake quite a bit and turn quite a bit, but you cannot do both at their individual maximum basically. Important to realize. As is drinking water. As is not buying eBay wireless mouse and keyboards. Anyways, the final thing about tires, so we had load and we had slip, is that the tire is also part of the suspension of the car. Sometimes when a car crashes, you see the tire bouncing off, and sometimes it sort of almost does a lap on its own as if it's magic. But that bouncing is basically because it is a spring, it's just a bouncy, springy thing. A spring is nothing else than something that if you put force on it, it compresses a little bit. And as we will do calculations, I have to give some rule of thumb. So that GT tire, we're going to do some GT calculations. You can tell about 17.5 kilos to compress that tire 1 millimeter, to make it 1 millimeter flatter. And the normal pressure is probably about 1.9 bar. So you can do the math and you get a tire that's about 33 kilos of load required to compress 1 millimeter. But that means if you go out of the pits with cold tires that are at low pressure, your tire is 25% softer. It's like having a 25% softer spring at low pressure, which is quite significant, especially these days with stiff suspensions in racing cars. If the tire's spring is 25% softer, that feels quite different. So the tire isn't just, you cannot disconnect the tire from the suspension. It's part of it, and its movement is just as important as the movement of the suspension. And it's also important when calculating stuff that we come to later. So we have load. Load sets the maximum theoretically available grip, and the grip increases, but not as much as the load increases. And you can only get the grip if you have the tire slipping. And we mentioned that they are springs. With that in mind, and if suddenly some of you think, well, wait, hang on, what about that? You can always ask, as I mentioned. With that in mind, I would like to go to the second topic, which is weight transfer. It's very important in racing cars. And this way I try to visualize what it is. What is weight transfer? So in blue, that's sort of a triangle. It's like a pivot point, a joint. And the black stuff, you see, it's like a steel bar. And the one on the left, I put an input force at the top there of 1. And it acts over a distance of 1. And then there's another distance of 1. And then there's the reaction. And the sum, if you multiply the input by the input distance, it should be the same, is always the same, physics, as the output distance times the output reaction. In other words, on the right there, if we apply that input at a shorter distance, the reaction force halves, because on the right we have 1 times 0.5 has to be the same as 1 times 0.5. Simple equality. If you imagine this, so the lower you apply this force, the smaller this reaction force will be. That's quite important. Here I made a drawing of a GT car, of which I'm quite proud. It almost looks like a car-ish. We do calculations, so we need some numbers. So I give it some wheelbase and width and the center of gravity height. Center of gravity is, without getting too deep into it, that's where those forces apply. So in order to slow down the car at 1G, we need 1250 kilos of force put on it, and that force will apply at the center of gravity. Just physics, that's how it is. And you can perhaps already see, we can translate this into the car. Now, I don't want to go too deep at it. With the math, it's fairly simple. But that ratio of distances, so we have 0.4 when the car is braking in a side view, the force applies at 0.4, and the reaction distance is 2.5. So that 1250 kilos of force becomes 200 kilos worth of weight transfer. It means the front tires both together gain 200 kilos and the rear lose 200 kilos. And what about cornering? Then you're leaning left and right instead of forward and backwards braking, for example. The distance is smaller. So a small distance is not good for weight transfer. And if you do the math there, we get more weight transfer, 333 kilos. And we already talked about tires. They don't like load, they don't like extra load. So weight transfer puts extra load on the outside tire when you're cornering, for example. Tires don't like that. If they could talk, they would probably complain about it. The reality is that you cannot do a lot about it. The regulations allow limited size of car, so you cannot make a 10-meter wheelbase car. It would be very good for weight transfer, but a 10-meter long car would be a bit heavy probably, so it's always a trade-off between regulations and technology. So it's a fact you have to deal with. Now this is the top view. Again, it's almost a racing car, very proud of that. Static, just with the car sitting on the ground in the pits. We decide it has an even weight distribution. Each tire sees 313 kilos of load. Just simply the 1250 kilos divided by 4 and then rounded, because of course it doesn't quite matter, but fine. Now we add the weight transfer. 333 kilos of weight transfer in a corner. That means the outside tires, in this simple example, they go from 313 up to 479. And we know that downsloping curve with the tire grip means we can get a force there, a maximum theoretical force of 728. That's great. On the other side, the loads get less because the weight moves from the left side of the car to the right side of the car. And we can also make a calculation of the theoretically available tire grip. Now, all this, what does this mean? Previously, with the car sitting still, it has a potential at each axle of just over 1,000 kilos of force. But now we're taking a corner and we're loading the outside tires, which they don't like. We only have 998 kilos of force available theoretically. So that's simply because we cannot avoid physics and the car engineers cannot put the center of gravity right on the ground. We lose 5% of grip simply because of the weight transfer that is required to make that corner. See, that's a good example of why weight transfer, how that works and how load sensitivity reduces the tire grip. Sadly, this is not quite complicated enough. I need a big sip for what's coming next. Now, normally when you set up your car in the racing simulation, most of the time the setup will be symmetrical. So the left side, if the front left is 100 spring, then the front right will be 100 spring. So the left rear is 150 spring, the right rear will be 150 spring. So that's an easy thing, but front and back are usually different. So the front might be 100 and the rear might be 150 spring. And in this example, the weight transfer I divided evenly over the front and over the rear. And this is where the trick comes in. Front and rear are not symmetrical. And it depends on the stiffness of the anti-roll bars and other things, how we distribute that load transfer. So that 333 kilos of load transfer, how much of that goes to the outside front tire and how much of that goes to the outside rear tire. This is a 3D model. I probably have to add that because it's a bit cheap. I do physics, not 3D models. Picture there's a very stiff front suspension. You can see a thick spring, and at the rear there's a thin, light colored spring. The car is taking a corner, so it has body roll. And you can imagine for every bit of body roll, the springs get compressed a little bit. Now, if you compress a really thick, hard spring, if you put 100 kilos of force on it, it will move this much perhaps. If you have a really soft spring, put 100 kilos of force on it, it will almost go to the ground, for example. But the body roll means front and rear have, simplifying it for now, but more or less equal displacement. But the force it takes to displace the front 2 centimeters is a lot higher than the force it takes to move the rear spring 2 centimeters. And now we have force again, so what happens? More of that weight transfer goes to the side with the stiffer spring. And that's interesting. We have to look at the tire, the regular springs and the anti-roll bar in order to make actual, factual, calculatable sense of this all. And I'm going to ignore something about roll center heights and suspensions. We'll do 2 examples. We're gonna put one setup on the car and then see what the weight transfer is, and then we'll put another setup on the car. First, just some numbers. Springs 10, anti-roll bar 10, and then some calculations, because basically the tire has a spring rate. It bounces around, so that is a spring, and the suspension sits on top of that. And this is a simple formula. What happens if you put 2 springs on top of each other? You don't really have to remember or know this, but we'll just assume this is correct, and I hope it is. I'm quite sure it is. The combined effect of the tire and the anti-roll bar and the spring is 12.5 kilos per millimeter. Just for now, let's assume that's correct. Rear suspension, we'll assume different values, and we get to a suspension rate of 10 kilos per millimeter. So on the front you need 12.5 kilos to compress the spring and the tire together 1 millimeter, and at the back it's 10 kilos. Typically at the back you see slightly softer anti-roll bars, for example, so this might be, a reasonable starting point. With this in mind, we know the spring rates and we have some numbers on the tires. We can see that the total of this together, 12.5 and 10, so the total stiffness combined is 22.5, just add them up. And the front is 12.5. So now you can calculate what is 12.5 of the total, 56%. So 56% of the weight transfer goes to the front and 44 goes to the rear. And now perhaps you're putting it together. Load, tires don't like load, the friction changes, and we're putting relatively more load on the front than on the rear. So the front will suffer more in grip than the rear. Now, doing the numbers here, I could run by this, but for now you assume, hopefully I didn't screw up too badly. The result is, to putting the numbers in, so we know the loads, and that means we know the potential grip that the tires have. The front axle now has 986 force and the rear axle 1013. So the rear axle now has a bit more grip than the front compared to before we started. Here we had symmetrical, so front 998, rear 998, and now we get the suspension stiffness with it. And we have less at the front and more at the rear. So we changed the balance of grip. The rear is now more grip than the front. One practical example, but now we're going to change the setup. So we still have the same springs, but at the front we install a much stiffer anti-roll bar, and at the rear we disconnect the roll bar. And you can forget about the math again, just assume that now the front becomes a lot stiffer, 18, the rear is about 8. So it's much more of a difference. Adding those up, 25.8, and that means how much is 18.1 of 25.8? 70%. So now 70% of that weight transfer goes to the front and 30% goes to the back. So there was even more uneven loading of the tires. This is the picture. So now at the front we lost even more. We now have a theoretical maximum available grip of 950, just a bit less, and at the back almost 1050. So we created more rear grip again. And we went from the rear having about 3% extra grip to the front to about almost 10% more grip than the front. So that's how it works when you change the roll stiffness of the car, which you can do with anti-roll bar, you can do it with stiffer springs, or you can add more tire pressure, which is a weird thing to do, but it would actually have the same effect. That's what creating a stiffer front does to the potential of grip on the front. And these are the first setup, and below it is the second setup. Did I go too fast? Are there any questions about that? Is it somewhat clear to you?
As long as it's clear in that situation you will of course a car that will understeer.
Yeah.
Then it's understood, yes.
Yeah. So that's the magic behind weight transfer, which is unavoidable, and tires not liking load, which is unavoidable, which means that the harder we load a tire, the less happy it is, and the more grip we lose on that side. And one problem with this is I'm forgetting about a lot of things. So I'm purely cornering, and we're not doing any braking or accelerating, and there are a lot of things I ignore. You don't even have to read it, just be afraid of the amount of stuff that's mentioned here. So it's extremely theoretical, but it is the evidence of why increasing the front anti-roll bar or the front springs changes the balance of the car, because there is simply less potential grip on the front as a result of that load sensitivity curve that goes down. Okay, now the next part, now we've had the tires and the weight transfer stuff, is how do you sort of drive with that in mind? And that's something I cannot create for you, but since all the grip and the handling of the car comes from the tires, knowing what they are doing is quite important, and it can probably help you understand why in some situations you crash on the left and why in some situations you crash on the right, for example. The answer is always in the tires. And this is something I totally stand behind. How often have we complained about a car that understeers? I have done it about 100 times, but it's always the driver that gives the inputs. So you can complain about the car, but at the end it's you has to make the most of it, and you should be as good as possible in minimizing it, but complaining about the car is not allowed in this session. Well, some of the time. So, what I have as an engineer, of course, and there are lots of ways to be quick in a simulator and in real life, but I'd like to visualize what happens if I brake and I turn in, what is Is there a high tire load, so a lot of potential grip, or is there a low tire load, and am I applying a lot of slip with a lot of steering, or a lot of braking, or just a little bit? That helps me understand that's where the root of the tire grip comes from. And that's what we're going to talk about now. I have two cases here. Typical things you see in sim racing as well as in real racing, where the solution lies, or understanding the problem lies in what we discussed with weight transfer and tire grip. So, understeer going to snap oversteer. Now, I've experienced this many times, and I've blamed the car many times. So, what happens? What am I talking about? Well, we saw that we need a bit of slip. Load sets the potential maximum grip. We only get it if we start to rub the tire over the road by steering, for example. If you apply too much steering, you lose grip. And that's where understeer comes from. So here's the situation. We have steering wheel angle on the horizontal, so now it's at 400, so the guy is doing this, turning in. He's way beyond the optimum. Optimum is about, in this case, 120, so turning like this would mean optimum grip. But the driver is not so skilled, and the car is understeering, so instead of keeping it here, he's not making the corner, so what does he do? He adds more lock. That's what he's just done. So he's got the wheel turned all the way, and then he comes back to the pits because he just spun, because I go on the throttle, and then suddenly the back steps out, and you have to fix the car setup. What's happening there, at least potentially, is imagine you're there. So you got this lock applied, lots of understeer, and you are way beyond the optimum grip. You feel the back end starts to slide. You think, I know this, I've got to apply opposite lock. So you start to unwind the steering. First step, you've unwound a little bit of the steering. What have you done? Increased the front grip. So you're sliding, you could oversteer, and now you get more front grip. What's going to happen? The oversteer is going to get worse soon. So your opposite lock isn't yet opposite lock, you're still unwinding the understeer, and as you do that, you still get more grip on the front, so you're making it worse. So things are getting a bit scary. Next step, still unwinding that steering. Finally, you've arrived at what you should have been inputting as steering in the first place. But you're still increasing as you're recovering the slide. You're not recovering it yet, you're still just getting rid of the understeer. So at this point, the back end is still sliding more, and you've still made it worse because you still have more grip on the front. So by now you're in trouble, basically. You might be 5 stick marks, as I recently mentioned. Only from that point, from the optimum, about 120 degrees, that last little bit, when you remove that steering, do you actually remove grip on the front of the car. But this process from going from here to here before you actually start to do anything is 4/10, I don't know. And in 4/10 the racing car can kind of do this. So this is a very typical explanation for people who complain about understeer, which goes to snap oversteer. It's just that they apply too much steering lock, which they first have to unwind before they start to correct the slide. So imagine a good driver. He has an understeering car, okay, but he knows the limit of the point where steering more doesn't work, where the grip starts to lose and get less. So he is pretty good, and he's got the wheel at 120 degrees, puts the pedal on the metal, and he gets oversteer. The instant this guy lets go of the steering a little bit, he reduces front grip. So he corrects the slide instantly. And there's no drama, there's no tank slapper, there's nothing going on, and he's better and quicker. That's an example. We talked about tire load and slip, of using too much slip and causing a lot of problems for yourself. And then finally I have another, how do you sense what's enough? That's a bit tricky. I tend to get it wrong. Everybody gets it wrong, so that's the good thing. But if you get it this much wrong or that much wrong, is still a big difference. You can look, we have triple screens, and if you enter a corner you see the trees go left and right. And if you're on a skid pad, for example, in iRacing you have that, or you have tracks for other simulators available, just look at the speed at which the trees go by, and you'll see that if you go from center to this, the trees will go like this. If you steer more, they go quicker, but at some point they don't speed up anymore, and that means you're not turning any faster. Well, that's a very simple way you could see it. But the best thing is using telemetry All modern simulators have telemetry, and it is a bit complicated, and not everybody wants to get into the technical side, but you can plot the g-force of the car and you can plot the steering angle. So the point where steering angle grows, but g-force stops, then you're applying too much steering. But that's not everybody wants to get into the theoretical sort of telemetry side of things, but the answer to all your problems lie in telemetry. That's basically the harsh reality of things. And of course practice, that's all the time the answer to everything in racing and sim racing. The more you drive seriously with your mind active, you will learn and you get a better feel for it. But this, I keep going back to it, even if the car is bad, you should not fall into this understeer trap. And we've seen guys in the simulator today, some are perfect and some think, oh, I'm not making the corner, what should I do? Steer more. And that's just not gonna work. Too much slip, it's a bad thing. And the final example, which often leads to the first problem, sadly. The cause of all these problems are, of course, a slight lack of skill or practice. Let's look at some telemetry. You know, it's Saturday afternoon, you're enjoying your time at the Nordschleife here to hardcore telemetry. We have three lines here. The blue one is your brake input, the orange one is your steering input, and the green one is the load on the outside front tire. So we're going to brake and turn into a corner, and we're looking at the tire load that is on the heavy loaded outside corner where you're leaning the most on. So here's a complaining driver. And what you see, he gets on the brake, the blue line rises, the tire load rises because you're leaning forward and the tire load increases. He thinks then, okay, I got rid of enough speed, let's go off the brake pedal. I think, well, now it's about time to steer it. So there is a sort of a dead zone, there's a moment where he doesn't do anything, almost. The problem with that is, he removes the load from the front tire. You see the green line dips as he comes off the brake and hasn't done any other thing yet. The tire load drops off. And if you have no tire load, you have no grip. So the grip potential this guy has, as he starts to apply the steering, right about here, the tire load is low. So he wants to enter the corner, but he has low tire load, which means fairly low grip. So he won't have the bite and the corner entry that he wants. Quite likely he'll have understeer. And that's the problem, so he enters the corner like this, and then he goes on the throttle, and then we already saw what would happen if you go on the throttle that way. So here the problem is, in the first problem we had too much slip, too much understeer. Here we have bad tire load management. He has a dip in the tire load. Good driver. This is how we like to see it. So a couple of differences here. This guy gets on the brake very hard, very suddenly. All modern racing cars basically is like this. You don't feed the brake in, the brake is it's like that. Hard and fast. He has that for a while, then he starts to slowly let go of the brake pedal. But he knows I want to keep load on the front tire, and if I just keep going off the brake pedal, the load will go down. So he starts to feed in the steering as he reduces the brake pedal. And you can see the tire load remains pretty high. So his grip potential on the outside front tire remains pretty high. So this guy enters the corner at a much higher speed, no understeer, and he wins. And already, I'll sum it up. Letting go of the brake pedal suddenly is a very common mistake I see with sim racer and amateur real races. You think, right, this is my braking done, and now I turn it in, and you have to combine it. And he applies the steering fast, and there's no load, so yeah. Another thing, he uses a friction cross instead of a friction circle. So what this guy does, he does the braking, straight line, and then cornering, and then lateral grip. And what the good driver does, he blends from braking into cornering. So if you have that friction circle, the first guy goes braking, done with braking, cornering. And the good driver brakes, slowly comes with adds cornering, he follows that friction circle. And that's the key. And I've seen telemetry for single-seaters and GT cars. It doesn't even really matter, this is basically the technique that works, keeping the tire load and keeping the potential grip on the tire. So yeah, these are the things that I explained. And finally, sadly, I am more than a second off the pace with guys like from Redline, Atze, perhaps you know Atze Kerkhoff.
1 second.
I'm very chuffed with myself because I set a good lap time. Atze comes into the office. Oh, you got a new car? Oh, let me have a go. And he does 10 laps and he's a second quicker. I'm not slow, but that guy is real quick. So at that point, there's a lot more for me to gain because he uses the same setup as me. He just has better inputs. He manages tire load and tire slip better than I. I'm too sudden off the brake, or I have too much turning applied when I enter the corner, too much slip, I get understeer. It's not in the setup in that case, it's all in the driver, sadly, so we are the weak point. But I think that the more you know about physics and tire load, and we've explained a couple of things of why we get understeer and problems, it might be on the back burner in your mind. Perhaps when you slide off the track, just like I do often, at some point it helps you to understand why that happened, and that knowledge is the basis for getting quicker in the simulator in real life. Setup tips I cannot give you, even though I promised, so sorry about that. But I try to think of all the setup changes that you do, what do they do to the tire load? And I've made some random examples here that are not necessarily even the best, but if you lower the ride height and you have a downforce car, lower ride height means more downforce most of the time, and that increases tire load. So a lower front ride height on many, at least single-seater racing cars, would mean more potential grip on the front because the tire loads are higher. So that's why lower ride height with aero can give more grip, for example. If you have a softer setup, and there's a lot of ride height variations as you drive around, you might get a lot of aero force changes, and that changes the tire loads, and that changes the potential grip of the tires. And we saw that with a stiff front anti-roll bar, we changed the distribution of the load transfer from the front to the rear, the ratio between that. You can change the grip that way. A lot of things you don't have to remember, these are not necessarily good things, but you see the process where I'm trying to translate the car setup change into, okay, what does this do to my tire loads? For example, if you use more power lock in your diff, there's the potential for the outside rear tire to get more slip, which might put more force on the road and you might get better acceleration or more oversteer. Well, I could go on forever. The last one is interesting too. If you have shorter gears, you have a bit more driving torque on the rear tires. It might just be enough to generate a little bit of extra slip and a little bit of extra acceleration. Everything can be translated back to the tire load and the tire slip and the tire grip in that case. But this is not something that's easily like second nature all of a sudden, but I want to give this insight because when you go online and you read car setup guides, you see add this to fix this problem, change this to fix that problem, and you don't learn anything from that. And sometimes I disagree with it because it's never as easy as click this to fix your problem. First of all, you are most likely the problem because you're the main contributor to changing the loads and the slip. That's what you do with your steering wheel and your pedals. But also just apply this to fix your problem and you don't know why. What have you learned? So what I tried today was to give you a bit of tire theory and weight transfer theory. So with an actual example, why grip changes when you change the front anti-roll bar, for example. You are probably confused by this stage, as am I, but I'm hiding it. I went through it relatively quickly perhaps, and I can imagine you have questions that they don't even have to be exactly about this. You can have anything that's on your mind, well, as long as it's, let's keep it in race car, sim racing themed. I'm not there for personal advice. But any questions about anything related or not related to this?
Would you mind sharing, could you send us this material by email if I send you a link on iRacing?
Yeah, we do. For 500 euros, you can. No, I'm recording it, so it will certainly go on YouTube.
Yeah.
The light is blinking, so it's still recording. Very good. And I may publish a PDF or something.
A PDF would be great.
Yeah, it's not hard to do. I have to get home and arrange that. So most likely, and you will probably see it on. I'll email like Virtual R or B Sim Racing or Race Department, you know, the vlogs and stuff. They probably put a link up to it if they think it's interesting enough to post anyway. And there will probably be a PDF of this, yeah. took me the longest time to find this picture of a cat. That was actually the most time-consuming thing about this present. No, I don't. Anyone else have a question of any kind?
Yeah, can we go deeper into it? Yeah, it's interesting, and it's just the top of the ice.
Yeah, that's true. Things I left out, for example, we mentioned that the tire spring rate is important and the spring rate of your suspension and the anti-roll bar, but actually the suspension geometry is also has a part in anti-roll basically. It's called the roll center height and it changes with ride height and that changes your roll stiffness, but it goes too far. But this was just about enough, and especially the calculations with the anti-roll bar change, the car setup change, to get a point across where you can understand why a setup change does something. Yeah. Anybody else has anything he wants to ask or share, or feel free, I'm here now.
Very interesting, Niels. Thank you, sir.
All right.
Learned a lot.
Then I will thank you very much for leaving the fun stuff behind and sitting in a classroom on Saturday afternoon. Some people would say that's not really healthy, but hey, thank you very much for being here and listening to me. And if at any time you have any questions, we're here the rest of today and tomorrow, if I still have a voice, I'll be doing it again at 12 in the afternoon. So thank you very much, and I'll see you around. Have fun at the expo.